break. I hope you enjoyed the snacks and the coffee and you're full of energy. We will continue with the next talk. This is the left pirouette, and with me is Andreas Vollner, and he will talk about exploit automation that is coming. Everybody has his fair share, I guess, with return-oriented programming and the problems, and I hope Andreas has a solution for us. Enjoy.
Now it's working, okay. Thanks for the introduction. My name is Andreas Vollner. I am currently a PhD student at TU Darmstadt, that's in Germany. And there I work at the Center for Research in Security and Privacy, also known as CRISP. But I'm originally from Vienna, so it's very nice to be back here. And my research interests are basically applied research in exploitation, exploit mitigation, binary analysis, reverse engineering, things like that. So you could say that I like staring at assembly code a lot. I have the word exploit in my title, so let me refine the scope a little bit. I will not talk about confused deputies. I will not talk about high-level Java exploits. I will not talk about Android permission exploitation. I will not talk about SQL, and I will definitely not talk about exploit kits. That's a lot of things I won't talk about. What I will talk about is good old memory corruption, more precisely return-oriented programming. Geht wieder? Okay. Return-oriented programming, also known as ROP, and more specifically, how we can automatically generate useful ROP chains. So we will look at quite a bit of assembly, and I hope you're not scared of that. Quick agenda. I'll talk about the past, the present, and the future, and I'll sneak in a few of my papers. In the past, I will just recap some basics, so we're all sort of on the same level. Stack smashing, data execution prevention, return-oriented programming, so just the basics. Then I'll talk about how we currently develop ROP exploits and about some mitigations against them. And in the future, I'll talk about some new attacks and some new mitigations that are coming up. So let's get started. Actually, the 10-year DeepSec is not the only anniversary, because almost exactly 20 years ago, LF1 wrote Smashing the Stack for Fun and Profit. That was on November 8, 1996, so almost exactly 20 years ago. And it's still a highly influential paper, of course. So just to recap stack smashing, we have a return address somewhere on the stack. And because the programmer, as always, forgot to check his buffer bounds, we have a buffer overflow, so an attacker can overwrite the return address, and if he doesn't write A's, so instead something useful like malicious code, and overwrites the return address with the address of that malicious code, he can divert the control flow and execute that malicious code. That stack smashing that uses a stack buffer overflow, nowadays those are pretty rare, and usually you have other attack vectors like use after free or type confusion. But if you're lucky, you might still find one of those today. Anyway, of course, that's not ideal from a security point of view. So smart people came up with something that's now widely known as data execution prevention, or DEP. And this enforces basically that memory is either writable or executable, but not at the same time. So if you think of your heap or your stack, those are writable. You store your user input there, so they shouldn't be executable most of the time. There are some exceptions, like dynamically generated code, but I'll cover that later. So yeah, data execution prevention basically prevents that the heap and the stack are executable. It's enforced in hardware, and it's now standard on Linux and Windows, and even Apple figured out they might be smart to do that. So it's also on OS X, iOS, and so on. But it only prevents the execution of injected code. So we can still inject the code, and we can still hijack the control flow. We just can't run the code. This is going to be important later. So data execution basically prevents this very simple attack. Now the question is how can we bypass data execution prevention? Instead of injecting code, we reuse existing code. And the most widely used technique nowadays is return-oriented programming, or ROP. And it works similar to this. So we take existing chunks of something and put them together in a new fashion so we achieve something that's useful to us. In more technical terms, we, instead of injecting code we want to run, we inject a set of addresses, which is fine because we don't need to execute them. Those addresses point to so-called gadgets, and a gadget is a usually short sequence of instructions which ends with a return, and due to the way the x86 architecture works, you can make those gadgets execute consecutively. I'll show you how exactly that works in a second. So let's say we have our stack here, and we have a bunch of addresses which point to gadgets injected. The stack is marked red, which means on one hand it's dangerous because it contains user controllable data. On the other hand, it also means it's not executable, so the user can't just inject the code and run it because we have data execution prevention. So the attacker injects a bunch of addresses. And then we have our blue or grayish areas, which are in some libraries, so basically they're executable code. And here we have our gadgets. And now, for example, the very first address on the stack is 10. This is not a realistic address, but it works for this example. And it points to this XOR RAX instruction, so basically this zeroes out RAX. And then we have the address of another gadget, this one, at address 50, and this is executed twice, and it adds 20 to RAX. So after those 3 gadgets execute, RAX contains the value 40. Now, we can debate whether this is any useful for now, but it shows that we can do pretty much arbitrary computations without introducing any new code to the system. All we did was inject addresses, and this is important. Return-oriented programming is usually Turing complete if you have a large enough code base, and papers have shown that I think 20 kilobytes of code is already enough to achieve that. So with return-oriented programming, you can do pretty much what you could do with injected code. So let's say our goal is to execute arbitrary code in the presence of data execution prevention. There are basically 2 approaches. We could write a pure ROP exploit, so we only reuse existing code fragments, and we hope that all required gadgets are available and that we don't get too much of a headache doing that, but it's very unlikely. What happens in reality much more often is that we still inject regular shell code, because we still can do that. And then we use return-oriented programming to call an operating system function to make that shell code executable. And for example, we have on Windows virtual protect or virtual alloc, and on Linux we have mprotect or mmap. This is the signature for virtual protect on Windows. It takes 4 parameters. The start address of the memory region where we want to change permission levels, then the size of the memory region where we want to change permission levels, the new protection level, so we want to get the read, write, execute rights, and lastly a pointer to some address where it can store the old protection level. So now our goal will be to invoke this API or a similar API using only return-oriented programming. Now remember, x86-64, which we concentrate on, passes parameters in registers. And on Windows, those are RCX, RDX, R8, and R9. On Linux, you have 2 additional ones, and the order is a bit different, but for now, we'll just talk about Windows. So what you usually do is you provide the parameters directly in memory too. So you mix your gadgets and your parameters, and that would look something like this. So we have the address of the gadget we want to execute, and right after it in memory, we have the parameter we want to load into the register. And of course, the easiest way to load this parameter into RCX is a simple pop RCX gadget, which then returns. And this triggers that the next gadget executes, and so on. So basically, we have a gadget and a parameter, and the next gadget and the next parameter. And in the simplest case, we can load all our registers using these simple gadgets. Then lastly, we call virtual protect. And somewhere else in memory, we also have our shellcode, which we can then execute. And this is basically how most modern exploits actually work at that stage. Then we're ready to rock and roll. In a slightly more detail, we have up here all our registers. Again, this is the stack, so user-controlled data. And then we have some code here. And this is the return address. Now, again, programmer forgot to check his buffer bounds, so the string copy is unbound and triggers a buffer overflow. Watch how the stack changes in the next step. Now this data is user controlled basically, and you also overrode the return address, of course, so you can initially hijack the control flow. When the return instruction triggers, first we'll remove some registers because we're not interested in all of them and they're just too confusing. So now we just care about those registers. And now we switch to assembly. Now that looks better. So let's say the last instruction of the vulnerable function does zeros REX for some reason. So REX is now 0, and next we execute the return instruction. So what will happen is we load this value into the instruction pointer RIP. And then the program continues at this address. And at this address we have, surprise, a pop RCX gadget. So what happens when we execute that is that wherever RSP points to, so that's this, that's the first parameter we want to load, will be loaded into RCX, like this. And then we have the return instruction. So we continue at another gadget, which does pop RDX. So we load another parameter into RDX, which is 1000, like that. And then we have another return, so we continue at the next instruction, which is this one. And this continues on and on and on, and a few moments later, we have initialized all our registers, which are used for passing parameters with the correct data. So remember that the parameters virtual protect takes, which is the address, which is in RCX, and that's the start of our shellcode. The size, 1000 bytes, which should be enough for our shellcode. The new protection level is 40, which grants read-write execute rights. And lastly, just some address where the function can store the old protection level, which also seems to be somewhere on the stack down here. So now we can call virtual protect. It will run, it will make the area where the shellcode resides executable, and we have basically achieved our goal that we can run arbitrary code and bypass data execution prevention, and we don't have to deal with return-oriented programming too much. So I hope that's sort of clear. Now I'll show you how we currently develop those ROP chains, and the ROP chain is basically the mixture of gadgets and parameters. So currently we will use some kind of tool like ROP gadget or the Mona script, throw it at some binary, and it will output a long list of gadgets like this one. The gadget density is about 200,000 gadgets per megabyte. So if we have a reasonably large code base, we have a few millions of gadgets. Next, we will have to go through those gadgets and look for patterns that help us load data from memory into our registers. And ideally, we would prefer such simple gadgets. And if we find those, that's great. If we don't, which is more realistic, then we will have to get a bit more creative to find those. So what we could do is we could allow additional instructions between the instruction that loads data into the target register and the return. So in this case, for example, we also load some other data into another register, and the others also basically do that, or we could have some arithmetic instructions or things like that. Finding such gadgets isn't that difficult because we can just use simple regular expressions and say, okay, we want to load data into this register, then I don't care what happens, and it has to end with a return. Another option we have is to look for semantically equivalent gadgets. So a gadget that basically does the same, but with different instructions. So for example, we could first load the data into RAX, and then write it from RAX into RCX and then return, and that achieves pretty much the same thing in this case. The second one loads the data into RBX first, then exchanges RCX and RBX. So we also have our data in RCX, and this is actually one long gadget, and it also achieves the same thing. You might not see it immediately, but trust me, it also loads data into RCX. But finding those gadgets will be much more difficult, obviously. So yeah, let's say somehow you have found all the gadgets you need. Now you're in the step of combining them in the right order so they don't interfere with each other. If you have simple gadgets, well, then it's all good, because if you just have pop, register, return gadget, then there's no interference. If you have complex gadgets, you're going to have a really bad time, though, because you have to imagine all the side effects gadgets have, how they interfere with each other. So it's going to be a lot of trial and error. So yeah, to summarize, if we have simple gadgets, it's not really fun because it's too easy. If we have complex gadgets, it's very tedious, so it's also not really fun. So creating gadget chains is actually never really fun, unless the first time or so, maybe, because you're happy, whoa, it works. So why don't we just automate the whole process? That's what we did in our research group, and we developed a tool called P-Shape. Don't laugh at the name. That stands for Practical Support for Half-Automated Program Exploitation. And in the case we find simple gadgets, we can do pretty much what I just said. So we look for patterns like pop RCX, pop RDX, and so on, put them in any order, and it works. So there's not really any logic, or not much logic behind it. But if we have complex gadgets, we need to get a little bit smarter. And in these cases, we use semantic summaries and smart permutations, which I will introduce in the next slides. So semantic summaries help us to find gadgets that do a certain task. So we don't look for patterns anymore. We look for gadgets that achieve a certain task. So let's say we want to dereference RSP and load that data into RCX. Pop RCX is, of course, what first comes to mind, and that works. But for example, this one also works. It has some side effects, like it overrides RAX and RBP and R10, but it still loads data relative to RSP into RCX. This gadget would also be valid, or this gadget, or this gadget. So many work. How we create our summaries is very technical. You can read the details in the paper if you want. Basically, we convert the assembly into an intermediate representation. Currently, this is the VEX, which is also used in Valgrind. Then we propagate read and write statements forward. And lastly, we just simplify it and flatten the expression that results out of that. So let's have a look at how our summaries look like. We have a pop RCX red gadget, and the summary for this, it's not really shorter, but you'll see why it's useful. You can read it just like regular assembly, basically. So RCX is RSP dereferenced. That's what the pop instruction does. And RSP will be increased by 16, by 8 because of the pop instruction, and again by 8 because of the red instruction. Now if we look at a different gadget like this one, again, RCX will receive the value RSP points to, and RSP will also be increased by 16 as before. So these gadgets are pretty much equivalent. Lastly, we have this gadget, which also initializes RCX with the value RSP points to, and RAX will be the value of RCX. So first we pop into RAX, and then we exchange the values of RAX and RCX. So we also load data RSP points to into RCX. And with those summaries, you can find those gadgets much simpler, because you can just say, okay, I want this expression, for example. And this is much simpler than having to look for this or this or this individually. But there's more. What I've just shown you, we call post conditions. So those are the conditions of the system after a gadget has executed. But sometimes it's also interesting to know preconditions, and those are conditions that have to be satisfied that the gadget can execute correctly. So in this case, we load data into RCX, but you also dereference RSI. So if RSI doesn't point to memory that is readable, this gadget will crash. And our summary shows that just so that the program is aware of it. I'm aware of the fact that this summary is actually longer than the gadget, but if we have a more complicated gadget like this one, the summaries are very useful, I'd say, because you have aliasing right at the start and lots of dereferences. So the summary definitely helps you find the gadgets you need much quicker. So to summarize the summaries, they tell you what the gadget does to the system state. You don't get any information how it does it, but we don't really care about it. We just want to get the job done. And it's a good representation to quickly find the right gadgets. So now we have the gadgets. Now we have to put them in the correct order. So first we can just run a filter on all the gadgets we found and say, well, we are only interested in gadgets that initialize our registers used for passing parameters. And then we have a lot of gadget candidates. But we can't just start randomly combining, because if we still have 100,000 gadgets, that will take some time to find the right combination. So what we do is we grade the gadgets according to their quality first. And we're trying to find the best gadget to initialize each register. We wrote a paper about that, and that would also take too long to explain here what our metrics are. But in essence, the best gadget is the one that has the fewest preconditions and side effects, and they should be not severe. And then we basically have some buckets with registers to initialize, with gadgets to initialize each register, and we have the best gadgets on top and the worst on the bottom. And what we then do is basically we take the first gadget out of each bucket, so that should be the best gadget, and then we start creating permutations. On Windows, we pass 4 parameters in registers, so we have a maximum of 24 combinations. So you can really create those permutations and evaluate whether they do what you want in a split second. On Linux, you have 6 parameters passed in registers, so you have 720 possible permutations, which also doesn't take more than a second. So let's say those are the gadgets we found, and these are the best ones for some reason. Putting them in this order won't work, as you can hopefully see even in the back. So first we initialize RCX, but then the next gadget already overrides RCX with a 0, so we don't really want that, obviously. And it gets only worse from there. And a working order would be, for example, this one. So first we initialize R9. Here we initialize RDX and leave R9 alone. Here we initialize R8 and leave RDX and R9 alone. And here we initialize RCX. So then we have a working chain of gadgets. Okay. Lastly, we have to satisfy preconditions, because the third gadget has the precondition that RBP plus some offset has to point to readable memory. So to make sure that RBP is also controlled by us or the user or the attacker or whoever uses it, we would prepend the pop RBP gadget or whatever gadget has the best quality, so it doesn't interfere with any of the other registers and loads RBP. And this would be an example for a chain we've created for Nginx. We have a few really nice gadgets, but R8 and R9 are traditionally much more difficult to find good gadgets for. And yeah, that's what happened here. And I think a human would, at first, definitely shy away from using long gadgets like that, because they're long, probably do lots of stuff I don't want. But if you just give them to the tool and it automatically does everything for you, then there's no reason to not use such long gadgets. Now you might think, okay, that's a reasonable idea. Probably lots of others have thought about this too. So there's probably many other tools which can do the same. There are many tools which say they can do it. Let's have a look. So we compared our tool to quite a few other ones. Just to go quickly through the columns, search indicates whether it's a semantic or a syntactic search. So whether it uses simple patterns like pop RCX, pop RDX, or if it uses something like our summaries. Auto-chaining indicates whether it has auto-chaining abilities. Semantic summaries says whether there is a better view for gadgets than simply listing the assembly instructions. And then PE and ELF, just which file formats it supports and whether it supports 64-bit. For the results, lots of red. Many tools use a syntactic search, so they won't find those gadgets I've shown you before. Many claim they can automatically chain gadgets together. None of the tools except for ours has the ability to show gadgets in a better representation. And many are simply old and outdated, so they don't support PE and ELF or don't support 64 bits. On top of that, we have bugs. Many bugs. We haven't actually tried out all tools, because if it can't auto-chain, then there's no reason to try it out for us. But those we did try out, we found bugs, and we informed the developers, and they also acknowledged those bugs. So yeah, if you look at the table, you might say, okay, ROP-C actually looks pretty good. It doesn't have the summaries, but as long as it can auto-chain, you don't really need the summaries. But the problem with ROP-C, apart from bugs, was that the developer said that ROP-C is a proof of concept, should be treated as such. Don't expect it to work on real programs. So that's not really that useful. We, on the other hand, evaluated our tool on real programs. We tried Chromium, Chrome, Firefox, Internet Explorer, Apache, Nginx, so quite a few real programs. And we succeeded in most cases. Sometimes the gadgets are simply not there, but when the gadgets are there, we succeeded. Okay, so you might be wondering, what about ASLR? I mean, most systems rebase their libraries nowadays, so we need to bypass that first. We looked into it too, but an automated bypass is not really possible yet, in our opinion, because there are so many different attacks which apply in different scenarios. Putting all of this together in one tool, we just skipped it for now. Maybe we'll look into it in the future, but for now you have to bypass ASLR yourself, and once you've discovered the base address of one library, then you can use our tool. What about other mitigations? Because currently, as you probably know, there's lots of research in mitigation techniques against memory corruption exploits. I've just listed a few here. We can deal with those that directly affect gadgets. So control flow integrity and heuristic-based drop detectors. And I'll get to those now. So heuristic-based drop detectors. Basically, the idea, about 2 years ago it started, was, well, ROP behavior is very different from your regular program behavior, right? You have short basic blocks because, well, we want simple gadgets, and we have many consecutive indirect branches because everything ends with a return. So this is what a ROP program flow would look like. We have an instruction, usually a pop register, and then a return, and that continues a couple of times. A real program, however, it does calls, it has longer basic blocks, it jumps somewhere, so it's really much different from return-oriented programming. So what we did, and many others too, we developed, we made Robocop, which monitors program execution and looks for those parameters. So basically, we monitor the length of basic blocks and the number of consecutive indirect branches. We used the PIN framework by Intel for that, which is a binary instrumentation framework. And we were able to reliably detect real ROP attacks, which we found in the wild. There are 3 or 4 similar approaches which also use those metrics. But of course, the problem is if the attacker knows that you're looking for that, he can just use different gadgets. For example, you just use gadgets which have the minimum length 5, and then you'll be able to bypass all these heuristics. And that's also what we did with our tool. And this is a chain we created for Apache. So as you can see, every gadget is at least 5 instructions long. And using this, you can very easily bypass all those heuristics. Not just ours, also the other ones. Another way would be to use heuristic breakers. These are simply very, very long gadgets which contain 25 or even 50 instructions. And usually, if you put that in every couple of gadgets, then you won't be detected. And the goal of such gadgets is to be very long, but also to clobber as few registers as possible. And with our tool, you can easily find such gadgets. For example, this is one I found with our tool. That's, I think, a bit over around 30 instructions. It only writes to memory a lot, but it doesn't change the content of any register. So that's a very useful heuristic breaker. Next is control flow integrity, or CFI, which is a very promising mitigation technique at the moment. The idea behind it is that we compute the control flow graph, or CFG, ahead of time, based on source code usually, and then you enforce that the program sticks to that CFG at runtime. And an exemplary CFI policy could be that the return instruction must always return to the caller. That's usually enforced through a shadow stack. The jump instruction must stay within the current function. There are some exceptions, but I won't cover them here. And that a call instruction must target a legal function as determined by the CFG. So if you know an indirect call could call function A, B, or C, then you enforce at runtime that it does indeed call A, B, or C. You still leave some leeway in here because the attacker could call one of those 3 functions that should not be called, but you definitely narrow down the possible call targets very much here. However, that has a pretty large performance impact if you do it correct, and it also requires source code if you want to be really precise. What happens a lot more in practice is that you have coarse-grained CFI, and here a return must return to any call preceded instruction. Jump must stay within the current function as before, and call must target the beginning of any function, so you don't compute which functions are legal targets. You can just call any functions, but you still have to jump to the beginning of a function, so you can't just jump within a function or something like that. It's obviously much faster. It doesn't need source code, so you can easily apply it to legacy codes or off-the-shelf products, but it's also less secure, of course, but still many implementations use it. And the number 1 attack vector in this case is this one, of course. So in our experiments, we found that when you use only call preceded gadgets, you lose a lot of gadgets, obviously, but you still have about 3.3% of gadgets that you can use. If you consider that your average program base contains millions of gadgets, that's still a lot of gadgets you can use. And in our experiments, we didn't really have any trouble succeeding just using call preceded gadgets. We also found a very interesting gadget in our experiments, and I'll show you that on the next slide. It's long, but I'll help you find the important parts of it. So this is for Linux, and on Linux, parameters are passed in registers: RCX, RSI, RDX, RDI, R8, and R9. And as you can see, they dereference RSP, RSP plus 8, RSP plus 10, plus 18, plus 20, and plus 28. So basically, you can use this one gadget, which is also call preceded, by the way. You can use this single gadget to initialize all your registers, and you will bypass the CFI, you will bypass heuristics. So yeah, that's a pretty interesting gadget. We're still making more experiments to see if those gadgets are maybe very common or not. Because it's very long, we assume that most researchers have missed it, because usually you concentrate on much shorter gadgets. So let's see at what lies ahead. So first of all, this is from the movie Asylum. Don't watch it, it's horrible. But it's set in 2150, and they still use ROP. So I guess ROP will still be around in a good 150 years. So I don't know if that's good or bad. But yeah, more seriously, there's a lot of research going on in mitigations and in attacks at the moment. So it's basically an arms race. So especially in academia, you have a paper that presents a great new mitigation, and at the next conference, you have an attack against that. Sometimes they concentrate on implementation issues, so that's not really a valid attack, but they still get it accepted. But yeah, that's what happens at the moment. And a few very interesting techniques are, so CFI I've just talked about, but Intel is actually going to put that into hardware. It's called CET, Control Enforcement Technology. Basically, they have a hardware shadow stack, and they also limit the jump and call targets using hardware. So that should be interesting. If they do it right, then this should completely prevent return-oriented programming. So then we'll just have to switch to jump or call-oriented programming, I guess. Yeah, that's CFI. We also have fine-grained ASR. So usually when we have ASLR, we just randomize the base address of a library. And with fine-grained ASR, we randomize within an executable. So we randomize on a function level and switch the functions, the order around, or even on a instruction level. Next, we have execute-only memory. So currently one problem is that memory that is executable is at the same time also writable. And this is often exploited when you use info leaks to bypass ASLR, because you can read code like it is data. And that helps you discover gadgets at runtime, because you can just read your code sections if you have the right functions available to you. And execute only memory enforces that code is not readable like data at runtime. However, we also have attacks against all of the above. So yeah, there's still a lot of research to be done. Regarding rob automation, there's not really much happening, unfortunately. We plan to continue our tool. Currently, it has some limitations, which I haven't talked about yet, but I will do now. So we currently can only use return-oriented programming, so all gadgets have to end with a return. We plan to extend it to jump-oriented programming and call-oriented programming in the future, though. Also, at the same time, our tool currently cannot handle gadgets that contain jumps or calls, or instructions that rely on flags, so conditional instructions. But we also plan to address that in the future. But even with those very simple approach, we were able to bypass CFI mitigations and other things like that and succeed in most cases. So yeah, I think that's pretty good results. So yeah, that brings me to the end of my talk. Thank you very much. And if you have any questions, I'll gladly answer them.